But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win, and the others too. We shall send to the moon 240,000 miles away from the control station in Houston, a giant rocket more than 300 feet tall, the length of this football field, made of new metal alloys, some of which have not yet been invented, capable of standing heat and stresses several times more than have ever been experienced, fitted together with a precision better than the finest watch, carrying all the equipment needed for propulsion, guidance, control, communications, food, and survival on an untried mission to an unknown celestial body, and then return it safely to Earth, re-entering the atmosphere at speeds of over 25,000 miles per hour, causing heat about half that of the temperature of the sun, almost as hot as it is here today, and do all this, and do it right, and do it first, before this victory is out, then we must be bold.
And so, on July 16, 1969, at 12:30 in the afternoon, Neil Armstrong, Buzz Aldrin, and Michael Collins set off on a journey that fulfilled President Kennedy's challenge to place a man on the moon before the end of the decade. Thousands of years of unanswered questions about our planet's only satellite, brought on by generation after generation of human curiosity, were about to be answered. What do we know about the moon? Where did it come from? And what more do we hope to learn? Apollo answered many of these questions for us, but also left the door open for many more. The world the Apollo astronauts faced when they stepped off the ladder of the lunar module was one of the most hazardous and challenging environments human beings have ever encountered. Temperatures on the moon's surface range from 253 degrees Fahrenheit in the sunlight to negative 243 degrees Fahrenheit in the shade. In 2014, NASA's Lunar Reconnaissance Orbiter even measured temperatures in excess of minus 400 degrees Fahrenheit in a crater at the moon's north pole. It is, as Buzz Aldrin called it, a celestial body of beautiful desolation. The moon lacks an atmosphere, and its surface is a total vacuum.
Of the unknown at Hadley, I realize there's a fundamental truth to our nature. Man must explore.
One thing you gotta stop and do, make sure to have fun too, because you're only probably gonna come this way once.
I was strolling on the moon one day, in a merry month of December.
Average gravity on the moon is only 16.6% that of the Earth's surface, or only 0.16 Gs. It was actually possible for astronauts to bunny hop across the surface, demonstrated here by Apollo 15 astronauts Dave R. Scott and Commander James B. Irwin.
Hey, boy. Or whatever you call it. I can't get my left leg in front of me.
Lunar gravity, however, is not consistent across the surface of the moon. It fluctuates from area to area. The phenomenon was discovered on the earlier Apollo flights when the spacecraft velocity showed inconsistencies crossing over certain areas of the moon. Utilizing the Doppler shift of the spacecraft, NASA was able to create a gravity map of the moon's surface in the late 1960s. In late 2013, NASA's Twin Grail, or Gravity Recovery and Interior Laboratory probes, unraveled the mystery of the fluctuations of the moon's gravity.
Copy, Cam. This is your plot. Thank you for that report.
The footage you see here was actually taken from the Grail A satellite at the end of its mission in 2013. Over 9 months, the two spacecraft mapped the surface of the moon, pinpointing the location of super dense areas known as mass concentrations. Combining this data with known maps of lunar impact craters, NASA determined the anomalies were caused by the impact of super dense asteroids on the moon's surface. The surface of the moon has a very distinct appearance which has captivated astronomers, astronauts, and casual observers since the dawn of time. The two most defining characteristics being the distinct reflective surface covered in particulate matter known as the lunar regolith and thousands of impact craters. The distinctive lunar soil covering the surface consists of fine grains of rocky material. Scientists have identified 3 distinct processes that led to its creation. The first is known as comminution, or the mechanical breaking of rocks and minerals by meteorite impact. The second, agglutination, or welding of mineral and rock fragments together by the heat of meteorite and micrometeorite impacts. The last method in which scientists believe lunar soil was formed was through solar wind spallation and implantation, the sputtering caused by the impacts of ions and high-energy particles. In addition to forming lunar soil, these processes change the appearance of the soil over time in a process known as space weathering. Interestingly enough, patches of red soil were found by Apollo 17 in the Taurus-Littrow Valley and green soil at Hadley Apennine by the Apollo 15 crew. Scientists believe these unique color variations were formed via volcanic activity in the years shortly after the moon's formation. The impact craters vary wildly in size, the smallest being microscopic, discovered on rock samples brought home during the Apollo missions, to massive, the largest being the Aitken Basin on the moon's south pole, measuring 1,600 miles across. This is the equivalent distance from London to Athens and is the largest visible impact crater in the solar system. When we consider the orbit of the moon around the Earth, we must take a few things into account. First, being Newton's third law. The pull of the Earth on the moon is equal to the pull of the moon on the Earth. We must also consider that the force of gravity generated by an object diminishes by the square of its distance from the object. The moon completes one orbit around the Earth every 27.3 days and orbits at a radius of 384,000 kilometers. The orbit continuously widens at a rate of 3.8 centimeters per year. This is because the moon's gravity is stronger on the parts of the Earth facing the moon and less on the core and opposing sides. The difference between high and low tide in our oceans depends on whether the moon waxes or wanes from new to full and back to new again. When the new moon or full moon closely aligns with the perigee or closest point to the Earth in the moon's orbit, it results in a supermoon with resultingly large tides referred to as perigee and spring tides. Because the tidal force of the moon is twice as strong as that of the sun, the tides follow the lunar day and not the solar. It takes half a lunar day, on average 12 hours and 25 minutes, from one high tide to the next, so we see high and low tide twice a day here on Earth. The phenomena caused by this gravitational interaction that causes our tides is known as a tidal bulge. Tidal friction is created by the tidal bulge being moved around the Earth's surface. This slows the rotational rate of the Earth and adds energy to the moon, widening its orbit. Because of this, a century from now, a standard Earth day will actually be 2 milliseconds shorter than it is currently. Lunar phases refer to the shape of the lit area on the surface of the moon as seen from the Earth's surface. As the moon completes its 27-day orbit around the Earth, these phases shift over time. Since the face of the moon is locked to the Earth via tidal forces, we constantly look at the same area which is sunlit depending on the position of the moon in its orbit. This data from NASA's Lunar Reconnaissance Orbiter spacecraft shows the moon cycling through its phases as it appeared this year. There are 8 principal and intermediate lunar phases, beginning with the new moon, in which the disk of the moon is completely obscured by the sun's shadow, and ending with the waning crescent, in which a small sliver of the left side of the moon is lit. Lunar eclipses occur when the moon passes directly behind the Earth and into its shadow or umbra. This can occur when the Sun, Earth, and Moon are aligned exactly with the Earth in the middle. A penumbral eclipse occurs when the moon passes through the Earth's penumbra. The penumbra causes a subtle darkening of the moon's surface. Partial lunar eclipses occur when a portion of the moon enters the umbra. When the moon travels completely into the Earth's umbra, one observes a total lunar eclipse. The moon's speed through the shadow is about 1 kilometer per second, and totality may last nearly 107 minutes. The moon does not completely disappear as it passes through the umbra because of the refraction of sunlight by the Earth's atmosphere. A solar eclipse occurs when the moon passes between the sun and the Earth and fully obscures the sun. This can happen only at the new moon, when the sun and the moon are in conjunction. In a total eclipse, the disk of the sun is fully obscured by the moon. In partial and annular eclipses, only part of the sun is obscured. There are 4 main types of solar eclipse. An annular eclipse, which occurs when the sun and the moon are in line. A hybrid eclipse, which shifts between a total and annular eclipse. A partial eclipse, which occurs when the sun and the moon are not exactly in line with the Earth. And a central eclipse, in which the moon's umbra, or antumbra in the case of an annular eclipse, moves rapidly from west to east across the Earth. The most commonly accepted theory about the creation of the moon is referred to as the giant impact theory. In this theory, astronomers hypothesize that the Earth was hit by a Mars-sized protoplanet called Theia approximately 4.5 billion years ago. This resulted in a belt of material left in Earth's orbit that quickly coalesced into the moon. In 2001, rocks brought back during the Apollo program were analyzed by the team at Carnegie Institute in Washington, D.C. It was found that they had an isotopic signature that was identical to rocks here on Earth, but significantly different from all bodies in the solar system. Researchers found that the odds of they having an identical isotopic signature to Earth were less than 1%, and so the energetic aftermath theory was formulated. This theory postulates that while the Earth and the proto-lunar disk were still hot and molten, they shared a common silica vapor atmosphere. This theory explains why the Earth and the Moon share rocks with similar isotopic makeups. In 1609, the astronomer Galileo Galilei of Florence, Italy, was the first to record observations of the Moon through his telescope. It was a commonly held belief at this time that the Moon was a perfect sphere. However, through his telescope, he was able to observe the shadows shifting in the Moon's craters, as well as the interface between the Moon's light and dark side, revealing the uneven contour of its surface. Because of this, he deduced the Moon was covered in valleys, plains, and mountains, much like the surface of the Earth. Galileo's revelations were shocking for the time and did not give solid proof that Copernicus' theory that the Sun, rather than the Earth, was the center of our solar system, but did indeed pave the way for gradual acceptance. Fast forward to the late 1950s and the beginning of the Cold War space race between the Soviet Union and the United States. In 1959, shortly after the success of Sputnik in achieving the first satellite in space, the Soviet Union successfully sent a probe to the Moon. Luna 2 was not meant to make a soft landing. It impacted the Moon on September 13, 1959, but was instrumental in the fact that it was the first man-made object to ever touch another world. The follow-up Soviet mission, Luna 3, photographed and transmitted the first ever glimpse of the dark side of the Moon. Of note to astronomers was the fact that the Moon's far side was almost completely devoid of Luna Maria, the very visible dark lunar plains on the light side. Although these missions prompted President John F. Kennedy to issue his challenge to place a man on the Moon in 1961, the Soviets continued their lead in lunar exploration for a time. The first probe to ever make a successful landing on the surface of the Moon was the Soviet Luna 9 in 1966, which proved that spacecraft, astronauts, and equipment would not simply sink into the dusty lunar regolith. This lead was to be short-lived. In 1968, after years of development of the Saturn launch vehicle and the aftermath of the training accident that claimed the lives of Apollo 1 astronauts, the Apollo spacecraft was ready, and the crew of Apollo 8, Frank Borman, Jim Lovell, and William Anders, became the first human beings to successfully orbit the Moon and return home safely to Earth. To this day, the Saturn V launch vehicle that took men to the Moon is the most powerful machine ever devised by humankind, and debatably the greatest engineering achievement in human history. Using over 500,000 gallons of liquid oxygen and kerosene, the first stage of the Saturn rocket produced over 7.7 million pounds of thrust, the equivalent to over 111 million horsepower, or 85 Hoover dams. The next two Apollo flights, 9 and 10, were both used to prove equipment such as the lunar lander and Apollo spacesuits were capable to withstand the rigors of landing on the Moon. These culminated with the first steps of humanity onto another world, when Neil Armstrong and Buzz Aldrin stepped off the lunar lander onto the Moon's surface on July 20th, 1969.
Houston, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
I'm going to step off the limb now. That's one small step for man, one giant leap for mankind. Beautiful view. Isn't that something? Magnificent sight out here. Magnificent desolation.
The Apollo missions continued into the 1970s, all subsequent missions performing lunar landings, the exception being the near disaster of Apollo 13, which was dramatized in the movie of the same name. Commander Jack Schmidt of Apollo 15 even found the time to pay tribute to Galileo, the astronomer without who we probably would not have the understanding of our solar system we have today.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? This proves that Mr. Galileo was correct.
The Apollo program was instrumental in our understanding of the formation of not only the moon, but also our own Earth. Many of the theories and scientific discoveries we've discussed in this video were made or proven during the Apollo program. The final flight to the moon and the last time man has set foot there was Apollo 17. Landing on the Taurus Littrow Highlands on December 11th of 1972, the mission took invaluable readings on the moon's geology, gravity, and far ultraviolet radiation emitted by the sun. This speech by Commander Gene Cernan were the final words spoken from the lunar surface.
Bob, this is Gene and I'm on the surface. And as I take man's last step from the surface, back home for some time to come, but we believe not too long into the future, I'd like to just let what I believe history will record that America's challenge of today has forged man's destiny of tomorrow. And as we leave the moon in Taurus Littrow, we leave as we came, and God willing, as we shall return, with peace and hope for all mankind. Godspeed to crew of Apollo 17.
Cernan's wish to see us return to the moon will not be fulfilled until 2021, when NASA's new Space Launch System booster and Orion spacecraft take us back. Orion is a reusable space capsule based largely on the theories learned during Apollo. It will take astronauts on journeys to deep space, the moon, asteroids, Mars, and more. What more will humanity learn when we return to the moon? We'll have to wait and see.